Did you know that after traveling for over 4 decades, the Voyager spacecraft are now so far away that a radio signal takes nearly a full day to reach them? That's over 22 hours for a single message to make the journey from Earth to Voyager, and just as long for a reply to return. These faint whispers from the edge of our solar system are the most distant communications humanity has ever received. Launched in 1977, these twin probes are humanity's farthest-flung emissaries. They were designed and built by a dedicated team of scientists and engineers who could only dream of how far their creations would travel. Their mission was initially to explore Jupiter and Saturn, capturing breathtaking images and invaluable data. But after their primary mission, they continued onward, venturing into the unknown, pushing toward the heliopause, the invisible boundary marking the edge of our sun's influence. What they found there challenged our understanding of our solar system's interaction with the galaxy. The data they sent back forced scientists to rethink what happens at the very edge of our solar neighborhood. These probes are extensions of our senses, reporting back from a frontier no human has ever seen. They are our robotic scouts, braving the unknown and sending back precious information from a realm where sunlight is just a faint glimmer. The data they transmit paints a picture of a dynamic boundary where the solar wind, a stream of charged particles from our sun, clashes with the interstellar medium, the thin gas and dust that fills the space between stars. Voyager sent back a message that was far more dramatic than expected. The transition from the solar bubble to interstellar space was not smooth, but marked by turbulence and surprises. Built with 1970s technology, they have endured space's harsh environment, surviving extreme temperatures, cosmic radiation, and the relentless bombardment of micrometeoroids. Their resilience is a testament to human ingenuity and the spirit of exploration. As they approached the solar system's edge, their instruments detected strange phenomena, unexpected changes in magnetic fields, bursts of energetic particles, and mysterious plasma waves, hinting at a major discovery waiting to be unraveled. This essay explores the shocking truth Voyager uncovered at this distant frontier, a place where the familiar rules of our solar system begin to break down and new mysteries emerge. We will examine the data that revealed a blazing wall of plasma, a superheated, turbulent boundary that was entirely unexpected and unlike anything scientists had predicted. This discovery has profound implications for how we understand our place in the cosmos, reminding us that even at the edge of our solar system, the universe is full of surprises, waiting to be discovered by those bold enough to listen to its whispers. To understand Voyager's discoveries, we must first understand the heliosphere, a vast protective bubble blown by our sun. Created by the solar wind, this bubble shields the planets from high-energy galactic cosmic rays. The heliosphere is not a perfect sphere. It is compressed by the interstellar medium, creating a long, trailing tail. Voyager's journey was our first opportunity to get an on-site report from this unexplored region. Inside, the environment is dominated by the sun's magnetic field and its outflow of particles. The heliosphere is our armor, a dynamic shield that breathes with the sun's cycle of activity. Voyager's mission evolved into a quest to map this protective bubble's structure. Scientists were eager to find its edge and measure the interstellar medium's properties just beyond it. Voyager was poised to provide the ground truth we desperately needed. The Voyager probes were launched in 1977, using a rare planetary alignment for gravity assist to accelerate to high speeds. Voyager 2 visited Jupiter, Saturn, Uranus, and Neptune, while Voyager 1 headed toward interstellar space. After their final planetary encounters, the probes sailed into the vast space beyond Neptune. The mission team had to be resourceful to keep the aging spacecraft operational. The primary goal was to reach the heliosphere's boundary regions. Scientists predicted Voyager would encounter 3 distinct boundaries: the termination shock, the heliosheath, and the heliopause. Crossing the heliopause would mean Voyager had left the solar system's bubble. The mission was a multi-generational effort to touch the stars. In December 2004, Voyager 1, then about 8.7 billion miles from the Sun, made a groundbreaking discovery. The spacecraft detected a significant and sudden increase in magnetic field strength, a signal that something extraordinary was happening at the edge of our solar system. This was not just a minor fluctuation, but a clear marker that Voyager 1 was approaching a new and mysterious region of space. Alongside this, Voyager 1 recorded a dramatic drop in solar wind velocity. This marked the crossing of the termination shock, the first major boundary of the outer heliosphere, where the solar wind slows abruptly as it collides with the interstellar medium. For decades, Scientists had theorized about this boundary, but now, for the first time, we had direct evidence from the edge of our solar neighborhood. The solar wind, which had been racing outward from the sun at supersonic speeds, suddenly hit a cosmic wall and slowed dramatically. Voyager 1's data confirmed this deceleration but also revealed unexpected complexities in the process. The transition was not as simple as models had predicted, hinting at unknown dynamics at play. The termination shock itself was not a fixed boundary. Instead, it shifted and moved in response to changes in the solar wind, making it a dynamic and elusive frontier. In 2007, Voyager 2 crossed the termination shock at a different location, providing a second set of invaluable measurements and confirming the boundary's ever-changing nature. After crossing the shock, the temperature of the charged particles was found to be lower than scientists had predicted. This suggested that much of the energy was being transferred to pickup ions, particles that originate from interstellar space and are swept up by the solar wind, rather than simply heating the plasma as expected. This surprising insight forced scientists to revise their models of the outer heliosphere. The Voyager probes had now entered the helioseath, a turbulent and chaotic region sandwiched between the termination shock and the heliopause, the very edge of the sun's influence. The data streaming back from this region was even more surprising and puzzling than what had been observed at the termination shock. Scientists found themselves confronted with new mysteries as the instruments detected unexpected spikes and fluctuations, challenging long-held assumptions about the nature of space at the solar system's edge. The Voyager probes were now venturing into the wild, uncharted frontier of our solar system, farther from home than any human-made object had ever traveled. They were truly pioneers, exploring a region where the sun's influence fades and interstellar space begins. The discoveries from the heliosheath would prove to be even more astonishing than those at the termination shock, setting the stage for the next chapter in humanity's journey to understand the cosmos. After passing through the termination shock, Voyager 1 entered the heliosheath, a turbulent outer shell of our solar system's bubble. The spacecraft found a region filled with magnetic bubbles and turbulent flows. Instead of smooth magnetic field lines, Voyager encountered a magnetic foam. These magnetic bubbles create a complex structure that traps and redirects charged particles. Voyager 1's instruments showed the solar wind's radial flow had dropped to zero, piling up against an invisible wall. This stagnation region hinted that the heliopause was near. Voyager 2, on a different trajectory, confirmed the turbulent nature of the region. Its data gave us a more three-dimensional picture of this complex boundary layer. On August 25, 2012, Voyager 1, after a journey spanning more than 3 decades and traveling over 11 billion miles from Earth, experienced a dramatic and historic change in its environment. This tiny spacecraft, launched in 1977, had ventured farther than any human-made object before it, pushing the limits of exploration and human curiosity. Its sensitive instruments registered a sudden and significant drop in solar particles, the charged particles streaming from our sun, and at the same time, a sharp spike in galactic cosmic rays, high-energy particles originating from outside our solar system. This dramatic shift in particle data signaled that Voyager 1 had crossed the heliopause, the invisible boundary marking the edge of our sun's influence, and had officially entered interstellar space, a region between the stars filled with material from other parts of the galaxy. The heliopause is the boundary where the outward pressure of the solar wind, a stream of charged particles from the sun, is finally overcome by the pressure of the interstellar medium, the thin gas and dust that fills the space between stars. By crossing this frontier, Voyager 1 became the first spacecraft to directly sample the material of our galaxy, providing scientists with invaluable data about the nature of interstellar space and the transition zone at the edge of our solar system. One of the most striking discoveries was that the plasma density outside the heliopause was about 40 times greater than inside, confirming that Voyager 1 had truly entered a new region of space. However, the magnetic field data Voyager 1 sent back was puzzling. Instead of changing direction as scientists had predicted, the magnetic field lines remained largely aligned with those inside the heliosphere, raising new questions about the nature of this boundary. Scientists now believe that the interstellar magnetic field drapes around the heliopause, conforming to the shape of the heliosphere and creating a complex layered boundary between solar and interstellar space. So while Voyager 1 had crossed into interstellar space, it was still under the lingering influence of our solar bubble, not yet fully free from the sun's reach. In November 2018, Voyager 2, following a similar path, confirmed these remarkable findings, providing a second set of data and validating Voyager 1's historic journey. The crossing of the heliopause by both Voyager spacecraft was a landmark moment in the history of exploration, marking humanity's first steps into the vast, uncharted territory between the stars. Voyager 2's instruments provided an even clearer transition across the boundary, strengthening our understanding of the solar system's edge and opening a new chapter in our quest to explore the universe beyond our sun. As Voyager 1 and 2 approached the heliopause, they detected an incredibly dense, superheated wall of plasma. This boundary layer, just inside the heliopause, was hotter and denser than predicted. The term fire refers to the plasma's high temperature, not literal combustion. The Voyager probes measured plasma density through oscillations triggered by solar activity. The frequencies indicated a plasma density far higher than anticipated. This superheated boundary presents a major puzzle. One hypothesis is that hydrogen atoms from interstellar space become part of this plasma layer. This blazing boundary acts as an additional shield against cosmic rays. It forces us to rethink how our solar system interacts with the galaxy. Our home is better protected than we knew, encased in a superheated plasma layer. The discoveries made by the Voyager probes have fundamentally altered our map of the solar system. The heliosphere is a dynamic, turbulent structure with a foamy, magnetic heliosheath and a sharp, superheated boundary. This new knowledge has sent theorists back to the drawing board. The heliosphere is a robust shield against deep space radiation. This suggests that similar astrospheres could be crucial for the habitability of other planets. The Voyager data provides a unique laboratory for studying plasma physics. By studying Voyager's data, scientists can refine their theories about universal processes. The edge of our solar system has become a Rosetta Stone for deciphering cosmic physics. The journey of the Voyagers underscores the value of long-term space missions. Their success argues for future missions to explore the pristine galactic environment. The Voyager spacecraft have transformed our understanding of the solar system's boundary. They journeyed through the heliosphere, crossing the termination shock, navigating the heliosheath, and piercing the heliopause. The most shocking discovery was the superheated plasma wall at the solar system's edge. These findings have rewritten our cosmic map. The data has provided invaluable insights into plasma physics. The legacy of Voyager demonstrates the power of exploration. The twin probes continue their journey, sending back data from interstellar space. Their power sources are expected to fail around 2025 to 2030. The data they have sent back has opened up new questions for future research. As we look to the future, we are left with a profound question: what other unknown frontiers await us in the galaxy?